Welcome back everyone to part 2 on convolutional neural networks on custom images. In part 2, really what we're going to focus on is this special object from TensorFlow Keras, which is called the image data generator. What you're going to be able to do with this class is feed it in the directory of where your actual image files are, and you'll be able to perform a bunch of manipulations on your images and then feed those new images to your model. Let's go ahead and explore this idea of manipulating images as well as flowing from a directory these new batches of files. Let's head back to the notebook where we left off last time. All right, recall last time we basically read in the data and we figured out what are the average dimensions of our images. Because when we feed these images to the model, we'll need to make sure they all have the same size. So picking out the average dimensions is probably a good idea. In our case, it was conveniently around 130 by 130. Next is image manipulation. So keep in mind, there's really just too much data for us to read in all this data at once. These files are much, much larger than the files we've been dealing with. Recall MNIST was basically 28 by 28. The Safar was 32 by 32. And even that small expansion from 28 to 28 to color images of 32 by 32 was a huge expansion in the amount of data. So that's 28 times 28 was 784 data points. And when we went to Safar, that was 32 by 32 times 3, one for each color channel, that was 3072. Our files are going to be even larger as we read them in. They're going to be 130 times 130 times 3. So now we're dealing with 50,700 data points. Because of that, we're not going to be able to just feed in everything at once. Instead, we'll have to select batches of our images. The other idea that we want the model to be able to overcome is the fact that it should be robust enough to deal with images that are pretty different from images that it's seen before. And one way we can do that is by manipulating and performing transformations on our images. Things like rotation, resizing, and scaling. To begin this entire process, we'll say from TensorFlow, .keras, .preprocessing, .image, import, and we're going to use the image data generator. Go ahead and run that. And then once that's imported, I would encourage you to actually call help on this object and take a look at the documentation for this class. There's definitely a lot going on here. This is a huge class. It even has kind of full examples of how to do this. But what I want you to do is just take a time to kind of read through this and see the different examples. You can also read about this on its online documentation page. But what we're going to do is basically show you the main idea of what image data generator is doing. So what I'll do is I'm going to create an instance of an image generator. We'll say image gen is equal to, and we will call our image data generator object. If you do shift tab here, you can begin to see the various parameters, and there are a ton of parameters that you can pass in here. Everything from feature-wise centering, sample-wise centering, brightness range, horizontal flipping, vertical flipping, pre-processing, etc. So there's lots of different things we can do here. You should also recall that when we were dealing with the MNIST dataset, we had 60,000 images. And 60,000 images is a ton of images, and that was for a very simple file type, essentially a very simple image. It was only 28 by 28. Right now, we have half of that size over our entire dataset. Our entire dataset is less than 30,000 images. So what we want to be able to do is to expand the amount of images without having to gather more data. We can't just keep grabbing blood cells from people. So what we can do instead is do things like take our current images and randomly rotate them. So something we can do is say rotation underscore range and set this equal to the amount of degrees that we can randomly rotate our images. So we can do something like 20 degrees. And for something like the blood cell, which is circular in nature, you can probably choose a lot larger than 20 degrees. But here I'm just showing you examples. The other things we can begin to edit are things like the width, shift, range. And this will shift the actual width of the picture by some maximum percentage. So if we say 0.1, that stands for randomly choose a value between 0 and 10%, or 0 and 0.1, to shift the width of the image. And we can do the same thing for the height. We can randomly kind of stretch these out. So we can say something like 0.1. Now you may be wondering, what are good values to choose here for things like rotation and shifting? It all depends on the kind of images you're dealing with. We're very lucky in our case that we're dealing with what are essentially blobs. So we can expect that future images of red blood cells will kind of look like these blobs. They'll be circular in nature, and they can kind of be stretched or squished in future images. So what we can do is probably choose pretty larger values here for things like rotation, width, and shift. If you're dealing something like facial data, you don't want to be squeezing or rotating faces so much that they're in unrealistic positions. For example, let's imagine you're making software for a video camera that will be trying its best to detect whether or not the face of a person is in that image. You probably don't want to rotate something 180 degrees because it's not useful for the camera to be able to detect upside down faces unless someone is going to be walking upside down in that camera's view. So those kind of ideas can help you choose reasonable values for these random transformations. Okay. The other thing we want to do is we want to rescale the image. So we can rescale it by simply normalizing it. If we take a look at one of the sample images we have, so let's take a look at, let's say, Paracel. So that was our image file there. Let's take a look at the image read of it, and let's take a look at the max values here. So in our case, they're actually already standard and normalized for us. But if they were not, let's say they went from 0 to 255, then I'd have to rescale by saying 1 divided by 255. In our case, it looks like these images are already scaled for us, so we don't need to normalize anything by the rescale factor. We can also check this on that uninfected cell that we had earlier. So the uninfected cell, let's make sure that's actually, I believe this is already an array from before. So we already have the uninfected cell. Let's take a look at it, check out its max value. It also looks to be normalized. So it looks like all the values fall between 0 and something less than 1, which is exactly what we want in our case. So the rescale factor, we don't need to worry about that. But if you did want to rescale, you would do something like 1 over 255. Okay, so in our case, we're already normalized. We don't need to worry about that. We can also do things like have a shear range. So shear means cutting away part of the image. And we can set that to maybe a maximum of 10%. We can also zoom in on the image. We have the option to randomly zoom in. So you can say zoom range 0.1. We can also do horizontal and vertical flipping. So for example, I can say horizontal flip is equal to true. So it will randomly allow for horizontal flipping. And then I have to figure out, well, how am I going to fill in the missing data? So one way of doing this is fill mode of nearest. So what I mean by that is if you're doing a transformation that essentially stretches out the image, how are you going to fill in that space? Are you going to leave it blank through some just padding with zeros, or are you going to take the nearest pixel values to it and then stretch it out with those pixel values? I would recommend choosing nearest. Okay, so we have this image data generator, and let's take a look at this uninfected cell again. So recall uninfected cell is this array, so I can say plt image show, and I have this uninfected cell. Let's see what happens if I take a look at randomly transforming this uninfected cell. And it may not be so obvious here because there's no point in the center. So actually, let's do this with the para image or the parasite cell. So we're going to come back up here, make sure we grab the right object. So we'll say plt imread paracell. So scroll up, let's choose one that actually has this point. It'll make it a little easier to see the transformations. So we're going to go ahead and say plt imshow imread paracell. Okay, so I have this paracell imread. Let's go ahead and set that to just be para underscore image is equal to imread paracell. That way I can just simply display parasite image. So I run that, it's basically the same idea. So what I'm going to do is take this para image, that's my array, and I'm going to say the following. Take my image generator object that I defined above and call a single random transformation. So it's essentially do a bunch of random transformations on it based off the restrictions that I set up here. So we already know this is what it normally looks like. When we're actually feeding in the data to the model, we're not going to feed it this raw image. Instead, we'll randomly transform the image. So, whoops, Let's actually see the random transformation by saying plt imshow. Run that. Okay, so here is now the randomized version of the image. Notice that we got some stretch, kind of like columns sticking out of the cell, and that's because through this random transformation, it looks like it got stretched out, and it filled in those values with the nearest pixel value. And then note, it was also rotated. Makes a lot of sense to randomly rotate images here because they're cells. They can be in any sort of rotational axes that they want. They can be floating around in their sample. So depending again on the actual type of images you're looking at, you're going to be playing around with these actual range values. Okay, so now with the fact that we can randomly transform these images, I can essentially augment my data set. I'm no longer restricted to just this single image from this cell. I can randomly transform this many times over, so if you keep running this, you'll see more and more random transformations. And this is a way of artificially expanding your image data set. Recall we had less than 30,000 images, but now I could do a random transformation on all those images and immediately double the size of my data set. Maybe I could do 5 random transformations, and now I've gone from something like 20,000 images to 100,000 images. So this is a really powerful tool that you have to keep in mind when you're dealing with kind of smaller data sets. And when it comes to convolutional neural networks, it takes thousands and thousands of images to get something that performs really well. That's why the MNIST dataset and that Safar 10 dataset were actually very large. Okay, so how do we actually set up our directories to flow batches from a directory? The way we do that is we say image underscore gen dot flow from directory. And then you provide the path to your training folder. So recall that this train path variable, if we come up here, was the file path to cell images train. So we'll say image.gen flow from directory train path. And when you run that, you'll notice it says, okay, I found this many images belonging to 2 classes. How does it actually know that? Well, it's because in order to use flow from directory, your files have to actually be organized in a very specific way. And we've laid that out for you in the notebook that corresponds with this lecture, working with custom images. If you scroll down, basically you'll see everything we've been doing so far. Keep going down until you see this. So in order to use flow from directory, you must organize the images in subdirectories. So this is an absolute requirement, otherwise the method won't work. So when you're following along with these instructions on your own data sets, the directories have to be basically like this. You have to have your overall image data folder. So recall that was our cell images folder. And then you need for every class here, so you have class 1, you'll go ahead and have an image. Another image of representations of class 1. Then for class 2, you'll need another image, etc. So essentially what happens is, if we take a look at our original training paths, so we can come back to our notebook to play around with this, recall that our training path is right here, cell images train. And inside of that, if I say OS list directories, I have 1 folder per class. If we were dealing with a multi-class classification problem, for example, let's say we were trying to distinguish between images of birds, dogs, and cats, then I would need 3 folders here. 1 for all the bird images, 1 for all the dog images, and then 1 for all the cat images. So you need a folder per class. That is how this flow from directory immediately understood that there was 2 classes, because there's 2 folders here. There's the parasite folder and the uninfected folder. So that's how this works. It must be in this sort of format. And you would then have 1 folder for your training data and then 1 folder for your test data. Okay, so now that we understand that, let's go ahead and see what it looks like for the image generation flow from the test set. We would just say image gen flow from directory, check out the test path, run that, and you'll notice it found 2,600 images belonging to 2 classes, which makes sense because there was 1,300 images per class. And again, the test path has the exact same formatting. It has 2 folders beneath it, 1 for each class. Okay, so that's it for this lecture on being able to generate images from this image data generator class object. This is a super useful class, and it basically does all the heavy lifting for you. I would encourage you to spend time reading the online documentation for it to see what other options there are. But the main thing to note here, and again, a big part of this is understanding your file paths, is making sure your data is organized into this particular format of one folder per class, where then every class folder has many instances of that particular class. So this would, for example, be all dogs, all birds, etc. for each of those animal classes. In our case, we're just dealing with 2 classes. Coming up next, we will create a model, and then after that, we'll talk about evaluating the model's performance. Thanks, and I'll see you at the next lecture.